do that you're going to have to do over and over and over again in this chapter. So first of all, we've talked about in chapter 4 proving triangles congruent. Oh, I messed it up. Give me a second. I messed it up. Go ahead on your notes while I'm pulling this back up and see if you can answer questions 2 and 3. 2 and 3. Yep, 2 and 3 on the warm-up. See if you can do those. I'm going to pull these back up real quick. Yes, solve the proportion. Okay, we'll come back to it. So if you're still working on it, stop for a second. Go back to, in your mind, chapter 4. Okay, chapter 4, we talked about this kind of a statement. And this was called what kind of a statement? Does anybody remember? Did start with a C, but it wasn't conditional. Congruence statement, okay? This whole chapter is not about proving shapes congruent, it's about proving shapes similar. So we're going to be talking about taking shapes, and remember we had one transformation that did not keep shapes congruent, dilations, and they made shapes bigger or smaller. But when the shapes get bigger or smaller, they're still similar, okay? So this chapter is going to be all about similarity. It's going to be applying it to a real-life situation like a blueprint and building a house. When you have a blueprint, your shapes are similar to when they are built. Angles that are 90 on your blueprint are 90 in the house. Sides on a blueprint may be 2 inches, but then when the house is built, they're 10 feet, but they grow by the same similarity ratio. So they enlarge by the same scale factor. Okay, so we're going to be connecting those concepts of relating what we did with congruence to similarity, and then the idea of transformations as well. So just wanted to remind you, when you see a congruent statement, that it tells you exactly which angles and sides match up, right? So Q is congruent to, R is congruent to, and S is congruent to. And then same with sides. QR is congruent to. All right, so you get the idea. So if they asked you to identify the pairs of congruent angles or pairs of congruent sides, it's just like what we did before. And we would just list them. Q is congruent to Z, R is congruent to Y, so forth. We're all good with that? Okay, and then the same with naming the sides congruent. You could draw a picture if you want to as well to help you. We're going to talk today about what's called a similarity statement, and it's going to have similar concepts, okay? Solving proportions, though, there's 2 ways you can solve a proportion. Some teachers teach you to multiply both sides by the denominator. Or what's easier if it's 1 fraction equals 1 fraction is the concept of cross multiplying. Have you guys seen that before? Okay, so some yes, some no. To me, if it's 1 fraction equals 1 fraction, it's going to be easier to think about it as just cross multiplying. So when you cross multiply, you do the numerator times the denominator and set that equal to the numerator times the denominator the other direction. So 8 times x minus 3. Notice I put it in parentheses because it is 2 times all of that and 8 times all of that. So what are we going to have to do? Okay, but to do that, we're going to distribute, right? So when I distribute, I get 6x minus 6 equals, distribute, 8x minus 24. So then we want to add 24 to both sides. Okay. So then that's going to give me 6x plus, is that 18? Yeah. Okay, equals 8x. Okay, then we'll subtract the 6x, good, and we get 18 equals 2x. Divide by 2, and what is x? 9. So when it says solve each proportion, it's just saying solve for x. You could plug that 9 back in and make sure that your proportion is true and that you did it right. What is 9 minus 3? 6. What is, it's all right. We all have a day. It just helps everybody else feel better. So 2 over 6, what does that reduce to? 1/3. So that means if we plug in 9 over here, we should get 1/3. What's 3 times 9? 27 minus 3? 24. What's 8 over 24? 1/3. So you can plug it back in and check it, but when it says solve, all it's asking is what is the value of x, okay? So same idea over here. I'm not going to take the time to work it all out, but I'll set it up. You would cross multiply. 77 times x minus 6 would equal 42 times 2x minus 14. Okay? And then you would distribute and solve. Is it okay if I stop right there and say, I know you can solve that equation? Okay. I want to warn you, though, when you get to Algebra 2 next semester, we'll be dealing with rational functions, and we will be talking about solving equations that have fractions, that have variables in them, like this. If you end up with something like 1 over 2x plus 3 plus 4x minus 2 over x plus 3 equals 5 over x minus 7, which we will. It's going to be fun. So when we get to this, you cannot cross multiply because you do not have a proportion. A proportion is one fraction equals one fraction. We have an addition problem going on over here on the left first. So you would first have to learn how do I add rational expressions, and then if you can get it down to one fraction equals one fraction, you can cross multiply. And we will talk all about that next semester. But I want to make sure that you understand, if there is a plus or minus sign here, do not cross multiply. Okay?
So the homework, I end up with that, I know I did something wrong.
Correct, because you're not going to have that right now. Okay. Is that okay? You guys with me on how to cross multiply? You're going to be cross multiplying all chapter. Like, it is huge. So I need to make sure you understand. One fraction equals one fraction, cross multiply. Okay. We will do it over and over again. So I already told you we're trying to figure out, are polygons similar? And then eventually we're going to be proving, writing proofs to prove them similar. Okay? It is not a heavy proof chapter, but we will do some proofs. Vocabulary, on this chapter, this will be our first chapter where we do not have a vocab test. Chapter 8 will also not have a vocab test. We will skip chapter 9 and put it at the end of the semester if we have time. And then we'll move on to 10, 11, and 12. So, and we won't do chapter 13 that's in the book. So the next two chapters for sure, you will not have a vocab test. And I'll talk more about what that's going to look like on the chapter 7 test later. There'll be vocab words on the test, but it won't be matching like normal. So I'll talk about it later when we have time. Okay, so what does it mean for them to be similar, and what is a similarity symbol? Similar, first of all, this is our symbol. So just like for congruence, you have an equals with a little squiggly, or equality, equations are just equals. Similarity is just the squiggly, okay? Figures that are similar are going to have the same shape, but not necessarily the same size. That's why a dilation is going to keep them similar, because they get bigger or smaller. Just one. One squiggly. Two squiggly means approximately. So if you're rounding, you should be using approximate symbols. Okay. So down here they show you one is similar to two because they look like the same shape, but one's just bigger. Here, one is not similar to 3. Notice 3 looks like it's a right triangle. 1 does not look like a right triangle. They are not the same shape, okay? So they have to be the same shape, one bigger, one smaller, to be similar. And this is how we can state that they're similar with a little similarity symbol or not similar. Okay, the majority of your homework in section 7.1 comes from this little chart here, and I have students every year who miss their homework questions because they don't really understand what they're doing up here. So I want to really be clear, and I would take some notes if I were you. So first of all, the definition for similarity that we're going to use all chapter long. Two polygons will be similar if, number one, their corresponding angles are congruent. That's identical to proving them congruent. If they were congruent, they had to have corresponding angles that were congruent. The difference for them to be similar is number 2. They have to have corresponding side lengths that are proportional, not congruent. So we're going to say this over and over again. If two shapes are similar, their corresponding angles are congruent and their sides are proportional. Angles are congruent, sides are proportional. Angles are congruent, sides are proportional. What we mean by that is, if I have a shape, and here's another shape, and I say they're similar, if this is 2 and this is 4, and this is 3, then this is going to be 6. By proportional, we mean 2 over 4 is the same as 3 over 6. 1/2 is the same as 1/2, so the sides are proportional. They reduce to the same fraction. Okay? The sides will not be congruent. The sides will be proportional. The angles have to be congruent. So if it's a rectangle, it has to stay a rectangle with 4 right angles. So good question, and we're going to talk about that when we look at some problems. It's all going to depend on how you've named the similarity statement. So I'm going to come back to that, okay? So you're with me? The 2 things, if you want to prove they're similar, corresponding angles have to be congruent, sides have to be proportional. We've got the definition. Okay, moving on. If they're similar, then you can write a similarity statement, just like a congruent statement, but notice the symbol is now a little squiggly instead of a congruent symbol. When you write that similarity statement, and I would probably add to my notes here, this is the similarity statement, because they're going to ask you to write it on the homework. And if they do, or on the test, you need to know, what are we talking about? What's a similarity statement? And they don't put it anywhere else in the notes. Okay? That similarity statement has the same properties as the congruent statement in that it tells you which angles are congruent. A and E are congruent. B and F are congruent. C and G are congruent. D and H are congruent, right? So when you get to the homework, they're going to say, list the corresponding congruent angles. And you're going to look at that similarity statement, and you're going to write down this part right here. Okay, so your homework is going to be a worksheet today. And the very first thing at the top of 7-1 says, identify the pairs of congruent corresponding angles. So you're going to do exactly what I showed you here. And then it says, and the corresponding sides. And this is the part that students get wrong. Okay, so watch closely for the sides. Sides are not similar. What are sides? Proportional. You will never put, so not congruent and not similar. You will never write AB is similar to EF. AB is similar to EF. You will not put that. Shapes are similar. Okay? Oh. Sorry. Shapes are similar. Sides are not similar. Okay? Super important. This is what I see all the time. Sides are not similar. The shapes are similar. Definition of similar is corresponding angles congruent and sides proportional. A side doesn't have corresponding angles congruent. Doesn't have angles. Okay? Sides cannot be similar. Sides are proportional. So the way you're going to write the homework, so this would be the first part, writing the angles. The second part on the homework then is writing the sides as proportions. And you can write it as an extended proportion. And I'm going to have you mark out this 1/2 right here, because that's not what you're going to write when you do this on the homework. And I'll talk about the 1/2 in a minute. So scratch it out so it's not there, so you don't think you're supposed to do that. When you write the corresponding sides, you're going to write them as proportions. So you're going to say AB matches up with EF. So AB over EF, that fraction should be the same as, and then you're going to pick another 2 sides, BC over FG. So BC over FG. And then you'll pick another 2 sides, CD over GH. So CD over GH. And then the last one I skipped was AD over EH. And this is what you'll write when it says list the corresponding sides. So these are our corresponding sides written as proportions. And these are the corresponding angles. And on the homework, that's what I'm looking for. Name the angles that are congruent, name the sides as proportions. Does that make sense? Okay, so back to what Javi said. This could be in the ratio of 1 to 2, or it could be in the ratio of 2 to 1, right? Just depends on which shape you start with. So what matters is the way your similarity statement is named, and this is huge for the test. Whichever one comes first is the one that has to go on the top. Okay, so the one that's named first has to go on the top. If you are saying that the shape ABCD is similar to EFGH, then the ratio is referring to the first one to the second one. So the number that was over here is called the similarity ratio. Please add this to your notes. Similarity ratio. Is it? Okay. So the similarity ratio is the number, not the names of the sides, but the actual number reduced. So if I looked at this picture and I named this one first, it would be 6 to 12 or 5 to 10 or 4 to 8, and they all reduce to 1/2. So if Javi names his similarity statement like this, his ratio has to be 1 to 2. But if Elena says, no, I don't want to do that, I'm going to name mine EFGH first is similar to ABCD, then her similarity ratio is 2 to 1. So it's how it's named affects what the ratio is. Either way, since we're talking about it as a ratio, ratios are fractions, so really it's better to write it as 2 over 1. Or the book will also do this, 2 to 1. So either way. Okay. Are we clear? Whichever one's named first goes on top? Okay, super huge. All right, so moving on. Here is where they talk about the similarity ratio and exactly what I just said. So ABC to DEF would be 1 to 2, but DEF to ABC is 2 to 1. Okay, so whichever one names first goes on top. All right, and a similarity ratio is always a number. I already said this, so I'm going to skip it and move on. Okay, so on the homework, the next thing that it's going to say is exactly what this says. Determine whether the polygons are similar. If so, write the similarity ratio. What's that going to look like? So it'll be the ratio between the sides, and will it be a number or a name of sides? Number. Your similarity ratio is always going to be a number. Okay? Like we just talked about here, 1 to 2. When you're naming the sides, you're naming the corresponding sides because you're trying to identify them. Okay, so similarity ratio is always a number. And then the similarity statement, that's when we name the entire shape similar to the entire shape, right? Are we good with those two different words? Okay, so it's going to say determine whether they're similar, and if so, do these two things. That's exactly what the directions are going to say here on this. Determine if they're similar, and if so, write the similarity ratio, name the similarity statement. Okay, so same exact directions. Okay, when we look at these two shapes, in order for them to be similar, what are the two things we're looking for? Congruent angles, not similar sides, proportional sides, right? Proportional sides. So first of all, what kind of triangles do we have here? Isosceles. So what does that mean about these angles down here? They're congruent. So if this one's 36, what are these two? Okay. So what is 180 minus 36 divided by 2? Is that 144? Yes. And then divided by 2 is 72 degrees. So each of these are 72. Is everybody with Ridley? Yeah, and remember, you can grab one every day when you come in, so you have one now, because the whole semester we're going to need one. All right, if I come over here, this is also isosceles, so what is angle W? 62. What does that make angle T? So Oops. And I'll come back to exactly what you said, Ridley, in just a second. So this is 124. Subtracted from 180 is 56. Okay. And Ridley said, I didn't go that far. I didn't need to because once she noticed that we had 72, 72, that didn't match 62. So we automatically know these shapes are in what? Not similar. Okay, so they are not similar. And if they're not similar, then you don't have a similarity ratio and you don't have a similarity statement. Okay? If they had been, though, I want to make sure we're clear what you're doing on the homework. So if they had been similar, I'm going to give this a name. If these were all right angles, I know, pretend it is. If they were all right angles, would these be similar? Because the corresponding angles are congruent, and because it's a rectangle, the opposite sides are going to be the same, right? So if this is 2 and this is 3 and this is 4 and this is 6, then they all reduce down to the same ratio. So you could either write A, B, C, D is similar to, how would you name the other one? Okay. And if you do that, what's your similarity ratio? Similarity ratio, remember, is the number of the sides reduced. It would be 1/2. And then again, if we switch the order, it'd be 2 over 1. Okay, so on the homework, if they are similar, it's going to ask you to write the statement, write the ratio. Are we really good understanding? Okay, somewhat. All right. So, yes, ma'am. Yes. So the shapes that have to have the little symbol in front are our triangle and our parallelogram. Those are the only two shapes that we've named that had a symbol in front of them. So if it's just a square or a rectangle, or if it's a pentagon or hexagon, you just write the letters in consecutive order. There's no shape in front. Okay? All right. So the last example you see here in your notes is kind of an application of what we're talking about. They want us to find the length of the model. Anytime you see the word scale or model, you're going to assume that the two shapes are similar. When you have a model car, if you actually buy a model car, it has been scaled down exactly identical to what the real life car would be. So if it's 1/32 of the actual size, every single thing on it is 1/32 of the actual size. Okay? So when you see that word model, you can assume and know that they are similar. Okay? Guaranteed. Okay. All right. That's right. If you buy a model car, it's exactly the same. Okay. So find the length of the model to the nearest 1/10 of a centimeter. So if we are comparing these two shapes and what we just learned, if they're similar, what's true about the corresponding sides? They're proportional. Love that you keep saying that word correctly. It's proportional. So we should be able to write a proportion and solve. In a proportion, you do not have to have the same units. As long as you have the same units in the numerator and then a different same units in the denominator, it will work. Okay, so you don't have to convert meters to centimeters or centimeters to meters. So what is one relationship, one pair of corresponding sides we have here? Okay, so 1.8 meters over 6.3 centimeters. And that should equal what over what? Make sure that you keep the units in the same spot, though. You could not say x over 5 or that would mess the whole thing up. Okay? As long as you do that, then you can just cross multiply and solve. So when I cross multiply, I'm going to have 1.8x meters equals, help me out, what's 5 times 6.3? 31.5? Okay. 31.5 meters times centimeters. And I'm keeping my units in my work so you can see what happens to those units. If I divide now by 1.8 meters to get x by itself, what's going to happen to the meters? They just cancel out completely, right? And our answer is going to be left in centimeters, which it should be because the model car is being measured in centimeters. So when I multiplied, I did 5 times 6.3 meters times centimeters. You do not, that's what I'm trying to show you. You don't have to convert as long as, Javi, you have the same units on one car and the same units on another car. Where you would need to convert is, let's say, for example, you were comparing two people. And I said I was 5'7". That's 5 feet 7 inches. That's 2 units in the same measurement. You can't have 2 units in the same measurement. So you would have to change that to either inches or a fractional feet. But as long as the entire shape is measured in the same unit and the other shape is measured in the same unit, then you can set up your proportion without having to convert them to the same units. Because what happens when you do that and you multiply, you end up with meters times centimeters. And then when you divide by your meters will cancel out. And you're left with just centimeters. Yes. Needles. I know. Are you following that okay, Javi? And I would like to leave it in there because when you're in physical science or you're in chemistry, how many of you are in chemistry or physical science? Okay, you will talk about units of measure a lot in chemistry, and you will talk about how they cancel and what your units should be left in. Yes. So the more you can practice that, the better it is than in chemistry. You don't have to include your units for me. I won't in your work as long as you have the correct units in your answer. Okay, that's fine. So I end up with x equals 17.5 in my units, centimeters. So again, you didn't have to include those units because you know your answer is going to be in centimeters. Okay? Second thing I want to point out is we did this side over this side equals the length over the length, right? We could have done 1.8 meters over 5 meters is equal to 6.3 centimeters over x. As long as you're comparing the same parts consistently in your fractions, you can rewrite that proportion a different way. So you can take that proportion and flip them both over and it's still true, or you can do numerator over numerator equals denominator over denominator and it's still true. Does that make sense? And the way you'll know is when you cross multiply, you should get the same equation. So when I cross multiply here, I still get 1.8x and 6.3 times 5. So it's still the same. It's not 2 over 1 because you're doing 5 to 17.5 and you're in different units. Okay, and with ratios, I love that you just said that, Tyler. With a ratio, if you want to know the similarity ratio, it has to be in the same units so that you can then simplify it down. You can't have different units. Does that make sense? So good question, I want to make sure everybody heard what he asked. If I said this was 2 feet to 6 inches, I cannot say that that's 1 to 3. I would have to convert to the same units first. So how many inches are in a foot? And 12 times 2 is 24. So it would be 24 inches to 6 inches, which is in what ratio? 4 to 1. Okay? So you can't give the similarity ratio unless it's in the same units. You can solve a proportion with different units on each shape, but you can't tell me that the similarity ratio unless you've converted them to the same units and simplified. Does that really make sense? I love that you said that. Thank you. All right, let's look at 7.2. You did? Did you figure out what the ratio was? Yes. Yes. Okay, so this is where we're going to talk about transformations again. And so I want us to review just really quickly all the different transformations based on the rules. So when we added or subtracted, what transformation was that? Translation in what directions here?
Right 3, down 1.
Good, right 3, down 1. And this is actually asking you to come up with what are the image points. So if you were to plug 2, 4 into here, what would you get? 5, 3. Okay, so I'm not going to worry about the point itself. I know you can do that, but I want to make sure we understand these rules again. What was it when X and Y did not switch, but Y changed sign? Reflection over what axis? X. Good. This is what I'm teaching right now in my other classes. What about number 3? What is it? Dilation, enlargement. Good. By 3 units. So when you multiply by the number, that's an enlargement. Or a reduction is the opposite, and if it is greater than 1, it's an enlargement, less than 1, reduction. So what is number 4 then? Dilation, reduction by 1/3. Okay, I'm not going to write it down. Those were our transformations that we talked about, along with what one's missing there. Rotation. Remember rotation, what we talked about is they switch and then change the sign, and it depends on the direction which one changes sign. So if we're rotating clockwise, then we change the one on the right. If we're going counterclockwise, we change the one on the left. Okay? So just reviewing that because you're going to use that in your assignment tonight. Okay, so we're going to draw and describe transformations in the coordinate plane. I don't think you will because I gave it to you on a worksheet, and they're already nice and graphed for you on the worksheet. So you won't, for this, yes, but for your homework, you're just going to have a front and back here. It's pretty short. Okay, so similarity transformations. Here is what a similarity transformation has to include. In order for it to be a similarity transformation and not a congruence transformation, to be a similarity transformation, it has to include one or more dilations. One or more. You could dilate it and then rotate it and maybe dilate it again. You could dilate it and then translate it. You could reflect it and then dilate it, but it has to have a dilation for it to be a similarity transformation. If it's just a rotation, translation, and reflection, or a combination of those 3, remember those produce congruent shapes. So it would not be bigger or smaller if you're just doing those things. So for it to be a similarity transformation, you have to dilate it. It can also include the other transformations as well. Okay, and then one thing I wanted to ask you is, what would 2 congruent shapes be similar? Say that again. Would 2 congruent shapes be similar? Okay, so this says for it to be a similarity transformation, it has to have a dilation. But that doesn't say for 2 shapes to be similar. Okay, so what was our definition for similarity? Angles have to be congruent, are they? Okay, and then the sides have to be proportional, are they? Is 2 over 2 the same as 2 over 2 the same as 2 over 2?
Yes. I think that last is a little bit
Okay.
off.
So what's the similarity ratio then if they're congruent? 1 to 1. So they are still similar if they're congruent with a ratio of 1 to 1. If they're similar, does that mean they're congruent? No. If you are similar, you could have a similarity ratio of 3 to 4. That's not congruent, right? So always, sometimes, or never question. If 2 shapes are congruent, are they always, sometimes, or never similar? Always. If 2 shapes are similar, are they always, sometimes, or never congruent? Sometimes. Because if they are similar, it could be that they're 1 to 1 similarity, but it may be 2 to 1 similarity. Okay? What do you mean? Oh, no. You just can't remember that. I don't have anything special for you. Okay, so a similarity transformation has to have a dilation. But for 2 shapes to be similar, they just have to meet the definition. Congruent angles, proportional sides. Okay? So we are going to look at some dilations. And this part should be stuff you already know how to do and should be really easy. Remember the directions back in chapter 4 when it says apply, you are going to graph. But on tonight's homework, it's already graphed for you. You are probably going to want some notes to look back at. So I would grab some graph paper real quick. I would, just so you at least have one example to look back at.
Almost. I just forgot to listen to the answers.
Okay. So I'm going to give you a minute to graph PQR. And that's all you have first. So just graph PQ and R. And then for time purposes, we're not going to graph the other ones, but remember they will be graphed for you on the filled-in notes that I send out. So if you need to click on that link when you're studying and look back at the graphs, you can. Okay, so I'm going to say this again. On tonight's homework, I'm giving you the graphs. But had it been, or in the future, if it says apply, don't forget that means you have to graph it, okay? And then you really wouldn't need the graph at all to identify and describe this. You should be able to look at the rule, because we learned this well in chapter 4, and automatically know that this is a dilation, which they tell you. But what kind of dilation? Reduction, and what is the scale factor? Okay, reduction by 3/4. I do want to remind you though, if you don't know what the scale factor is, if it's centered at the origin, then you can just compare the coordinates, and that's if it's just a dilation. So, for example, it would be -6 over -8 reduces to 3/4, right? Okay, so I need to review a couple things with you. That only works if it's centered at the origin, which means if you're not sure, the way we can check, again, back from chapter 4, is connect your pre-image to your image, pre-image to your image, pre-image to your image, and wherever they all cross is your center of your dilation. Do you remember that? Okay, so obviously this one's centered at the origin. You can only write a rule if it's centered at the origin. So we know since there's a rule it's centered at the origin. The other thing we wrote in chapter 4 is how do I find the scale factor? It's the image distance over the pre-image distance. I don't know if you remember that or not. If not, write it down. If you want to find the scale factor and they don't give you a rule, which is highly likely on your homework tonight, you have to take the image distance and divide it by the pre-image distance. Image goes on top. Okay? So if it's not centered at the origin, you cannot just compare the coordinates. So what I mean by image distance over pre-image distance is look at your shapes. Here's the image in red. What's the distance of this side of the red triangle? Let me erase all those markings. What is this distance right here? Yes, from -6 to +3 would be a total of 9. Okay, then compare it to the pre-image. What's the total distance on the pre-image? 12. What does 9 over 12 reduce to? 3/4. So if they don't give you a rule and you aren't centered at the origin, so when you connect them back, you're like, nope, they're not going through the origin, then do not look at the coordinates. Go back, look at the distances of their sides. Okay? If it's centered at the origin and it's only a dilation, you can compare the coordinates. Okay, but I agree. I think just distance is safer all the way around. Okay. Yes, sir. If you needed it, but since those were horizontal, we could just count them. If it's not, if it's diagonal, you'll have to use distance formula. When you're graphing, yes, you would name all the image should be with primes, the pre-image should not. Yes. Other questions? Okay, so on this one, I'm not going to have you graph it. Let's just look at it real quick. Determine if the two polygons with the given vertices are similar. Okay, so we talked about they have to have congruent angles and proportional sides. So first of all, when you look at these two shapes, do they have congruent angles? Yes, because they're all what? 90 degrees. A vertical and a horizontal makes a 90-degree angle. Now we need to compare their sides and see if they're proportional.
You said that the image goes over the
Mm-hmm.
How do we know which is which?
So we're going to assume, first of all, it's not asking you to give the similarity ratio, so it wouldn't matter. But if it was, I would accept either answer. So if you do 1/2 and somebody else does 2-to-1, you're both going to be correct. Okay? All this is asking you is, are they similar? So you need to compare their sides now. What's the distance from here to here? 9. What's the distance from here to here? 3. What about the other side? So if I go this direction and here, and so these are what shapes? Squares. And so 9 to 3 is going to reduce to 3 to 1. So they would be similar because all the sides are proportional and all the angles are congruent. So the answer would be yes. You will have some on your homework that just say tell whether the figures are similar, and the answers are just yes or no. But then the ones on the back on the bottom are going to say determine if they're similar, and then I wrote in list the transformations. So I'm going to make you write the rule that would prove that they are similar. If they're similar, what transformation do you know for sure is going to be included? Dilation, right? If they're getting bigger or smaller, it has to be dilation. So let's just do this one real quick. If we say yes, this would be x comma y arrow. What is our rule? We didn't, yes, sorry. So 3x comma, not plus, 3y. Or if you went the other direction, you could have had what number here? 1/3 x, 1/3 y. So what will help us if we're comparing answers is to assume the first one listed is the pre-image and the second one is the image. That's what we did in chapter 4. I won't count it wrong though. If you went the other direction, I'll still give you credit. It's just if you're trying to compare with the back of the book or with me, the answers may not be the same. Does that make sense? Okay, last thing is what happens if there's more than one. So here's what I want to show you. Notice when we compare the coordinates, 3 to 1 is 3 times bigger. -6 to -2 is 3 times bigger. If you were to draw all these lines in, image to pre-image, they're all crossing, oops, that was really bad. They're all crossing at the origin. Okay, so let's look at one that doesn't have that characteristic really quickly. So I want us to skip ahead. Not this one. Yes, actually this one. This one. Okay, this one. So skip to this one. Oh, I went too far. Stop. No, we're not going to take the time to graph because we don't have time. But if you need the graph, just know that it's on the filled-in notes and you can look back at it. Okay, here. Okay, so, oh my goodness. Please stop. Just stop. I'm afraid to touch anything. I thought so too, but then I touched it and then it did something different. Am I at the spot now where it's, okay, now it's doing what I want it to do. Okay, this one. Okay, so you look up here at the board, but only looking at the blue. Okay, only looking at the blue. The red's not there. All we have are the blue. Those are the things that are given to us. FGH and whatever that is, TUSV or TUVS. We have the two blue shapes, no red one. When you look at these two shapes, do you agree that this is obviously going to be a dilation of some sort? Okay. I can't. I've tried for 20 years. I cannot see how to look at them and decide where to reflect, where to translate, where to rotate until I do the dilation. I have to dilate first. Some of my students are brilliant. You guys will be just like them, and you'll be able to reflect, rotate, or translate, and then dilate. I can't do it. I don't know how you see it. So when I look at this problem and we're going from the big one to the small one, right? We're going to say the first one's the pre-image, the second one's the image. You don't have the red. Pretend it's not there. Okay? No red. If you graphed this, you would only have the blue. Okay? So what I'm going to do is say, how do I get the blue to look like the little blue? So then we're going to compare our side lengths to see what's the dilation, scale factor. So what is this distance here? 3. What is that going to compare with? T and S. So what is that distance? 1. Okay? This bigger distance, how far is it? From 3 to -3 is 6. How far is this distance? 2. Okay, so we're saying 3 to 1 or 6 to 2. So do we agree that 3 to 1 and 6 to 2 is the same? Okay, so what is my scale factor here? How much is it dilated? Okay, good. Because I did big to small, but it's not supposed to be big to small, right? If this is the pre-image and this is the image, we're supposed to be doing image over pre-image. This didn't get 3 times bigger. What did it get? 3 times smaller, so my image, my scale factor is actually 1/3. Okay? K is the scale factor. Yes. Yes. So when we write our rule, we are actually doing a reduction by 1/3 first, right? Okay? So now the question is, if I reduce this, it's not going to land here. Okay, so let's do that. Let's reduce this by 1/3. Take every coordinate and multiply them by 1/3. So what is G prime going to be? 1, 2. So everybody with me, we're just dividing by 3, multiplying by 1/3. What is F prime going to be? 1, 1. What is H prime going to be? 3, 1. And what is J prime going to be? 3, -1. So now you're going to have to plot those points on your graph paper. So I'm going to plot this so we can see it. So if I go to 1, 2, I'm right here. 1, 1, 3, 1, and 3, -1. So now here is my shape. It's the same shape. So now what do I need to do to get it to land on the little blue one? Reflection across the y-axis. So when it says, is it a determine whether the shapes are similar, I'm not going to let you just put yes or no back here because it says list the transformations. So you're going to write the transformations down as a rule. X comma y. What was the first transformation we did? Dilation, reduction by 1/3. So this is going to be 1/3 x comma 1/3 y. And then we took those coordinates, so keep your arrow going. And what did we do? Reflected across the y-axis, which makes which variable negative? -x. And so we'll put yes, these are similar, and this is our rule. But I can't see the red is they did the reflection first and then dilated, which I could see it maybe on this one. I can see that I probably need to reflect the blue shape over. But when it's a rotation or a translation, I can't figure out how far to rotate or translate. I just can't see it. So if you can switch the order and do it differently. For me, it's easier to do the dilation, graph it, and then figure out what to do from there. Okay? The only thing we didn't do was the circle, right? And so if you look at the circle one just real quick, I think you'll be fine. But what would we have to do to make the A land where the B is? We're going to have to dilate it. How far? Enlargement by how much? This is 3, this is 1, so it would be an enlargement by 3. But if I enlarge it by 3 centered at the origin, that just makes it look like this. So now what do I have to do? Translation. And how far? Exactly. Okay? So all circles will be similar. Okay? So, compass. All right, I didn't make you a slip this time since it's just a worksheet. And you'll have some time tomorrow, probably after your Aspire test. And I didn't leave anything extra for you to do other than just finish your homework, okay? So. I mean, I could